Right, hello everybody. Oh, microphone over here. Hello everybody, and welcome to this week's video, in which we will be doing some operator algebra. Um, More specifically, we will actually be doing basic operator algebra, because I don't really think I've sort of done that. We in introductory QM, in quantum mechanics, we tend to treat it all as differential equations with this wave function. Um, but really, there's a better way, much better way of realistically, it's a far superior method of understanding quantum mechanics, and it all comes from operator algebra. So rather from looking at everything through, because our wave functions with respect to x, right? Rather than doing that, if we take away from this position and we sort of look at how operators manipulate vectors in a Hilbert space, we can, like, complex systems just trivialize, which hopefully will show. Um, so we'll begin. Um, we'll do a few things. And the first one is, let's talk about Hermitian operators, or linear Hermitian operators even. So QM has physical observables represented by linear Hermitian operators, which act on a Hilbert space. And there's a very important thing here, is that not all of these operators in fact, these operators do not commute. That is definitive. And we have something called the commutation canonical commutation relation, CCR, which is, so we have our two basic operators. We have x, which is our position, and we have p, which is our, not to be confused with mathcal p, or however you do that, which is parity, but this p is our momentum. Those of you may see where this is going, but we have a useful relation between these two in the scope of operator algebra, and today, now, I'm going to write an operator equation, which I have done in the past, but I haven't really explained what they are. So, this operator equation, what does this mean? Okay, so this is the commutator function over here, and it's, if we have, so say we have a comma b, this is ab minus ba. Now, if you were to take two commutative units, they have to be unary. You can't have binary functions. But if you just take two commutative unary operators and put them in here, this would be equal to 0. If this is not equal to 0, these two operators, these two unary operators, are not commutative. That is that is a law of operator algebra, very important one. Obviously, if this is 0, then the commutator function says they do, or the commutator operator says they do commute, and the commutators say they do not commute if this is non-zero. Thus, by intuitive visualization, this x and p clearly do not commute. And thus, what does this tell us? Well, we know it's the Heisenberg uncertainty principle. It is absolutely impossible to measure the observables x and p to arbitrary precision. Okay, let's look at some more rules of commutators, and we're going to derive these. So first of all, we'll do let's compute a BC. It's a useful one to have, and you'll see why. Well, what's this going to be? It's going to be ABC minus BCA. Now, we must treat our operators not as a regular algebra, but as an operator algebra. And so you'll see how that matters. What we can do, though, a useful trick is we're going to add and subtract identical terms in the middle here. So we'll do ABC plus minus BAC plus BAC minus BCA. Okay. And of course, our plus and minuses are basic binary operators, so they don't apply under this unary operator algebra, so we can continue. And factorize out things, we are able to pull them out because they're both on the left side here, This is a homomorphism, and this one will be an epimorphism. Left cancel. No, this is an epimorphism, is right cancellation. Left is homomorphism. So we can say AB. This was then AB minus BA with C to the right side plus B AC minus CA. And of course, AB minus BA is going to be AB, the commutation of AB, times C plus B times the commutation of AC. And we can then again prove this by symmetry. So we have that A comma BC is this, and then also ABC is going to be ABC plus ACB. Nice. And these are some useful fundamental rules of operator algebra. And now we can flex this. Let's try then xp squared. This is back, so this is again x as our position and p squared as our linear momentum operators. So this is simply x p times p, which then plugging this into our first is going to be xp times p plus p. AC is going to be xp. We've already computed xp commutated, which is going to be IH bar plus p IH bar. Now we're working in a regular algebra, so we can combine things as we like. Those should already be in brackets. So this is just going to be 2 IH bar p. You can then go further and prove that. I'll leave this an exercise to you. If you're interested, then this becomes NIH bar p to the n minus 1. This is a mirroring of the standard calculus, of course. What does this look like? Well, it's a derivative. Yes, isn't that wonderful? Yeah, we see that the CCR then functions as a derivative in this case, where our power is the thing being derived. Now what we will do is look at the quantum harmonic oscillator. So this is a standard. I can't remember what book I learned about this from, but it was chapter 8. Sorry, it's very hot. I must drink water. I can't remember what book I learned about it from, but it was chapter 8, and that was the quantum harmonic oscillator. And I've never liked chapter 8 ever since that. I'm joking. But we'll first look at the classical Hamiltonian. So our Hamiltonian H is p squared over 2m plus half m omega squared x squared. Right? This is, I think, fairly understandable, but we are working in quantum mechanics now, so we can promote these to that's not very good, is it? We can promote these. That's now capital P, and that's now capital X, and so we have that it is p squared over 2m plus half m omega squared x squared. This is a slightly gross second order differential equation. What we can do instead is use something called ladder operators. So we'll have two dimensionless non-Hermitian operators, and these will be our ladder operators. We'll call them A, which is defined as root m omega over 2h, bar, 2h bar, times this whole thing, x plus I over m omega p. We have a linear combination of our position and linear momentum, and now we'll also define, I guess, would you call it the transpose of A? I never even thought of what to call it. A stake. Sorry, this has become greatly curious. How do you pronounce? Let's see. Is it telling me? Oh, a dagger. Okay. Well, you see, it would be the Hermitian adjoint, but A is non-Hermitian. I'll just call it a dagger. That's okay. A dagger is then going to be m omega over 2h bar, and this will be x minus I over m omega p. And now we ought to derive something useful using the CCR, which is, well, what is, I mean, we're doing operator algebra, let's just cut to the chase. What is a dagger? What is the commutation of this? Well, it is simply, am I going to run out? I will. 2h bar, x minus I over m omega p, plus even, and then m omega over 2h bar, x minus I over m omega p. Great. We can simplify things by pulling out this m omega 2h bar term because it doesn't depend on anything, so there's two of them, so it'll be m omega over 2h bar, x plus I over m omega p, comma, x minus I over m omega p. Wonderful. And, well, x, oh wait, no, we have more to do. Well, we'll expand this out using the linearity of our commutator. And we know xx and pp is 0, and that will actually just become h bar minus I over m omega I h bar. No, not that step yet. I'm thinking too far ahead. This will just be x comma p, because of course the other terms are going to be 0 plus I over m omega p comma x. Right, that's good, and now we can substitute in the obvious things. That doesn't commutate, so it's going to be minus sign, so m omega over 2h bar. I'm going to skip through the writing out all the algebra. Well, actually, yeah, I can skip through all of that. So that's going to be 2h bar over m omega, and this is simply 1. Lovely. So a dagger commutates to be 1. Or the commutation of them. So let's find what the actual product of them is, and knowing this will be fairly useful. Okay, so if we do a dagger A, in that order we'll have m omega over 2h bar, x minus I over m omega p, x plus I over m omega p. I'm sure you can see why these functions have been chosen as they are, judging by the fact that the commutation of is 1. They're very useful. And then we can m omega over 2h bar. We can expand, of course. I'll let you work out what that is. It is in fact x squared plus 1 over m squared omega squared p squared plus I over m omega, and we're going to have this xp, which comes from our derivations up top, and we can multiply everything by h bar omega, I h bar, on both sides, so h bar omega a dagger a. They do multiply by. Sorry, getting ahead of myself again. So this is still going to be m omega over 2h bar times x squared plus 1 over 2m h bar omega plus, sorry, p squared minus half. That's just by subbing in that this will be, and then the minus 1, and then omega over h bar. We can pull it out, right? And now we can multiply everything by h bar omega. So we have h bar omega a dagger a is equal to half m omega squared x squared plus p squared over 2m minus half h bar omega. And we can see here that this is clearly Monsieur Hamiltonian. So we have that h bar omega a dagger a is equal to h minus half h bar omega. And we can nicely refactorize, so pull that to the other side and pull out. So we have that h is equal to h bar omega a dagger a plus half. What do we call this? In fact, this operator, we tend to call it n. And this is the number operator. And h is just a linear function of this. Obviously, it's mx plus c. H is equal to h omega n plus plus h bar omega over 2. Well, it is fairly clear then that solving for eigenvalues of n gives you eigenvalues of h, which is lovely. Hello, what are we up to? Why do we keep being silly? That's alright. Now the last thing I want to do in this video is to derive the useful energy spectrum using nothing but our commutation relations, and interestingly it looks however like that. I wonder why that come from. Anyway, so how can we find that? Well, we're gonna keep using that creation operator, that a dagger that we had before. So what do we actually do here? Well, first I'm gonna take this Hamiltonian, this commutation rather, with the Hamiltonian and our a dagger, and that is gonna be h bar omega a dagger a. I'm going to keep using these creation operators, by the way. Half a dagger, and this is going to simplify. It will be h bar omega a dagger a dagger. Hey, look, something that seemed unexpected that I did earlier in the video comes in use. Well, how do we do this? This is going to be h bar omega a dagger a comma a dagger. Look, something else I did earlier in the video comes in use. Isn't that crazy? It is important to know that the commutation of any unary operator with itself is just 0. Obviously, an operator commutates with itself, especially in this case. And so we have that this is h bar omega a. That's 1, 1, 0. So that goes away. And thus we're left with this. Well, operator algebra is going to get really, really beautiful in a second. We're going to take an energy eigenstate, which is going to be the output this outer product. Hello, there we go. And it's going to have an eigenvalue en. So h ket n is equal to en ket n. And this is our energy eigenstate. What is the energy of the state? So what is I'm sure you're all waiting. I'm sure you're all shouting at the screen. What is the energy? What is the energy of the state A dagger times n? Well, let's try H on this and see what happens. That is, of course, the use of the Hamiltonian. So H A dagger n. What happens here? I'm sorry, it's just not having a good day, is it? Silly computer. We can pull this inside, and so we have H A dagger n. And we can start to do some useful commutation-y stuff. So then we can substitute in that H A dagger is A dagger H plus H bar omega A dagger. This may seem stupid because this is making my expression bigger, but you will only have to wait and see momentarily as to why this is actually the coolest thing ever devised. We can actually pull that and put it out there. Take out the A dagger, of course, and this is going to be H n plus H bar omega A dagger. Yeah. I forgot to close that bracket, sorry. Well, it looks like we're starting to have something vaguely useful here. We're aware of this because we have it up there. This is then A dagger E n plus H bar omega A n. What do you know? This is E n plus H bar omega A dagger times our energy eigenstate. This is kind of a profound result because we found that A dagger times our energy eigenstate n, that is also an eigenstate of our Hamiltonian. But whoa, it's been raised by exactly H bar omega. So what we find is that by multiplying by some factor of a dagger, we actually reach the next energy level exactly by this factor of H bar omega. The Hamiltonian consists of squared Hermitian operators. This must be positive, of course, because square it's real. And so there must exist n equals 0 where this can't be lowered anymore. So let's find out what that is. So if we then do H0, well, we have H bar omega A dagger A plus half times this state eigenstate of 0. This is going to be H bar omega A and then we get that this is half H bar omega 0. Oh, I forgot the obvious thing here, which is the half H bar omega 0. There you go, that goes away, and we're left with this. And interestingly, this is our initial state, this is our common ratio. Have we ever heard of AR? Oh, what is it? Dots is the thing, or dinos, the difference initial somethings, n. Oh, I forgot. but it's that. And we end up with this final expression for our energy spectrum ladder to be H bar omega n plus a half, where n is 0, 1, 2. Well, this is a pretty wicked result, isn't it? Now, if you were to find this result using methods of differential equations, you would not be a very happy person. But it is I think truly astounding how really simplistic it is to find out that kind of thing through the means of operator algebra. And on that note, I hope this was a useful introduction to why operator algebra is so blooming amazing. And I hope you have a very nice week, and I will see you next week for a new video. Bye bye.